Hi doctors, how are you? Welcome to a NotebookLM, where you can have fun while studying. Yes, trust me, it's fun to study with this kind of material. But before we proceed, the AI tools are amazing if you give it reliable information and you confine it within a good boundaries, a small boundaries. If you give a lot of information, you ask general question, it will be not so reliable. Okay, so I try my best to make each chapter in our course to one chat. So each chapter one chat, one chapter one chat. So last week we had this insanely annoying dental material topic like the physical properties. So let me take it as example just to understand. As you can see, each topic has its own chat. So here when you go, this is the sources. I give it to the chat so you can ask any question here. And this is a simple way of dealing with AI. What I really like about this, you have more than one way. So the audio overview is the podcast you have in your course. The video overview is the last minute video you have in your course. Sidekick, it can give you a presentation, extra presentation. It can do a mind map. It can give you a flashcard, and you can adjust the flashcard, standard, fewer, more, medium, hard. If you would like to discuss specifically about one topic, it can do that. I don't want to waste your time. I would like you to play with it. I will share the link with you so you can request access, because before I used to send invitation for everything and doctor are confused. I need this one, I need that one. So moving forward, I will give this one in the full course group. Then you can go through it. I like this topic. I will request access. I will give you the access. The magic start now. So this is the podcast. Let's try to intervene. Let's try to discuss with the podcast how I have a confusion about like the difference between brittleness and toughness. So let's try to ask him. Maybe he can answer us. Okay, I would like to understand the difference between brittleness and toughness.
That is a great question.
Oh, absolutely. Toughness is a really critical mechanical property.
And it relates directly back to those bonds we just discussed.
Right, we haven't explicitly covered that term yet.
But the way materials handle pressure, that's where toughness comes in.
Think of toughness as a material's ability to absorb energy before it fractures.
So it's about resistance to breaking, basically.
Yes, a tough material can bend, deform, and absorb an impact without immediately cracking.
Like how much abuse it can take before catastrophic failure.
Exactly. It's often contrasted with brittleness.
Brittle materials like a glass or, say, some ceramics might be very strong.
They resist initial deformation, but once they reach their limit, they shatter. They have low toughness.
Low toughness because they can't absorb much energy past their elastic limit.
Whereas tough materials like some metals or strong polymers can deform a lot before failing.
They absorb that energy slowly. That cloud of electrons in metallic bonds helps make metals quite tough and ductile.
Ductile means they can stretch and deform without breaking.
Hey, yeah, what's up?
You are great, but I would like to have dental perspective. Tell me, like compare enamel to dental. Which is tough, which is resistant, which has toughness, which has brittleness.
That is a fantastic follow-up question.
Okay, let's unpack this and get right into the dental perspective.
If we compare enamel and dentin, they are structured very differently.
Enamel is extremely hard and mineralized, almost entirely composed of hydroxyapatite crystals.
Because of that high mineralization, enamel is very strong, but also quite brittle.
It resists a huge amount of pressure initially, but if you push it past its limit, it will shatter or fracture.
So enamel has very high stiffness, but comparatively low toughness. It's brittle.
Here's where it gets really interesting. Dentin, the layer beneath the enamel, is different.
Dentin has organic components, mainly collagen, mixed in with the mineral structure.
This makes dentin softer than enamel, but much tougher.
It acts as a shock absorber. It can deform and bend slightly under pressure.
This allows the dentin to absorb energy and prevent the overlying brittle enamel from fracturing during chewing.
The toughness of the dentin essentially protects the strength of the enamel.
That's the beautiful, complex design of the natural tooth structure.
Dentin resists the crack Oh yeah, go on.
Nice. So add resilience now to the equation. Connect between resilience, toughness, and brittleness.
Oh, that's a conflict addition.
Absolutely. Resilience, toughness, and brittleness are often linked.
Okay, let's unpack this new term, resilience.
Resilience is related to energy absorption too.
But it's about the energy absorbed only within the elastic range.
Exactly. It's the ability of a material to absorb energy and then spring back.
So it absorbs the energy without any permanent deformation.
Think of a spring bouncing back perfectly to its original shape.
If you push a material past that resilient limit, it starts to deform permanently.
That permanent deformation phase is where toughness really takes over.
So resilience is an initial temporary absorption of energy.
And toughness is the total energy absorbed, including that permanent deformation, before it breaks.
Brittle materials like enamel have
Oh, back to our listener.
So
What's up?
enamel is brittle, dentin is tough, and resilience. Like if you compare resilience from enamel to dentin, which of those has higher resilience?
That is a wonderful, highly specific question.
You are connecting all the dots perfectly.
To compare the resilience of enamel versus dentin,
We need to remember that resilience is the ability to spring back.
and it's about absorbing energy in the elastic range.
Enamel is incredibly rigid, almost entirely mineral.
Because it's so stiff and brittle, its elastic range is very small.
It reaches its maximum energy storage very quickly before it fails.
So despite its strength, enamel actually has relatively low resilience.
Dentin, however, with its organic collagen structure,
Is more flexible and less rigid.
it can sustain more elastic strain before reaching its yield point.
This means dentin can absorb and release more temporary energy.
Therefore, dentin has higher resilience than enamel.
It's the shock absorber we mentioned earlier.
That resilient dentin protects the brittle enamel above it.
A great way to think about it is that enamel is stiff and brittle, while dentin is tough and resilient.
Perfect. That comparison is key for understanding biomaterials.
Okay,
Okay, let's
thank you.
weave that powerful connection.
Nice. So I hope you can catch the way we discuss it. So again, you can do this with all the topics. I will give you the links so where you can ask about it. Yeah, before we move on, let me ask about implant because we have a very tough question here from implant. Let's see how it will respond to.
Welcome to the deep dive. Today we are... Oh wait, someone wants to join. Hey, go for it.
So there is a term called black triangle in dental implants, specifically in anterior region. Tell me why this happened and what is the recommended distance from the bone to soft tissue, how I can avoid this to happen to my patients.
That is a phenomenal question.
A truly excellent interjection, E.
Because that specific issue, the black triangle, is exactly what makes anterior implant placement a nightmare, as the source material puts it.
Okay, let's unpack this for E.
The black triangle refers to the gap or space visible between the bottom edge of two adjacent crowns near the gum line.
It's the absence of the gum tissue, the papilla, that should be filling that V shape.
Exactly. When that papilla doesn't completely fill the space, light gets through and you see that dark triangle.
And Ace is why it happens.
It happens because the soft tissue, the gum, is fundamentally supported by the bone underneath it.
The height of the bone dictates the height of the papilla.
Precisely. The source material gives us the critical numbers here.
The distance from the interproximal bone crest to the interproximal contact point of the crowns is key.
The recommended ideal distance is between 3 to 5 millimeters.
If that distance is maintained, the papilla will most often completely fill the space.
But if it increases, say, to 6 millimeters, the risk of a black triangle goes up to 45%.
And at 7 millimeters, the risk jumps to 75%.
So to avoid it, you need to ensure the bone level remains high and the crown contact point is positioned appropriately.
It's a vertical dimension problem, and the integrity of the bone around the implant is crucial.
He also asked how to avoid it.
Beyond controlling the vertical space, the material stresses the horizontal dimension.
Yes. We need to leave adequate horizontal bone around the implant, especially between the implant and the adjacent tooth root.
The source material suggests the implant should be at least 1.5 millimeters away from the adjacent tooth.
Ideally 2 millimeters. Less than 1.5 millimeters leads to vertical bone loss.
And vertical bone loss dramatically increases that critical bone to contact distance E asked about.
Which means a black triangle. So proper spacing, both horizontally...
Yes, I hope now you can understand how you can interact with this one. And again, you can go back to this like infograph, like even giving you a tables about it. They give you, it's nice. I really love to play with this material. I will share you the link with the doctor and the full course, and I will give you access. See you soon.